Alright, first video for Physics 11H. I'm just going to shift my board a little bit here. I'm going to give you a basic introduction of motion. Um, I think we all have a concept of speed, especially in terms of, driving a car 55 miles per hour or running a race. Usually we think of miles per hour for a speed, right? Um, we often think of just the time it takes to go a fixed distance, like a 10-second 100-meter dash or whatever it might be. So let's look at a marker here rolling across this whiteboard, right? I let it go, speeds up a little bit in the beginning, but then it goes at a fairly constant rate across the whiteboard, just kind of fairly steady once it gets going. I'm going to draw a picture of the motion from the side view. All right. So there's the whiteboard, right? Here's the marker side. And it's rolling along, going a certain distance, about the same amount every second. It's moving to the right. So I'm going to draw a little arrow. The arrow kind of represents how it's moving, right? Those arrows, they're pretty consistent length. It's traveling about the same amount of distance each second, right? It's that's kind of the definition of speed, right? I'm gonna write it over here. Speed. It's kind of the distance covered in a certain amount of time. You guys know mph, right? Miles per hour. Well, in physics, we would write that miles per hour, right? Typically, we actually use meters per second. All right, I'll show you in class how big a meter is. So meters per second is typically what we would use in class. I got the little glare down here, so I apologize for that. There's another term in physics called velocity, and we will introduce that once we do our first lab. What I want to do really quick is make a graph of this object's motion. But before I do that, I need to introduce a concept called coordinate systems, okay? Coordinate systems, or system. All right, what's a coordinate system? Well, it's kind of like it's a way to tell where something is located relative to some point in space, right? We have a coordinate system on the surface of the Earth, right? Latitude and longitude. Maybe you can think of other coordinate systems, right? Battleship, B7, A3. That's a coordinate system. Really, what a coordinate system needs for in physics is two things. It needs a reference point, ref point, which we call the origin. All right, this is going to be like our zero location. All right, where we say the location you are at 0 meters. So our origin in this physical system is going to be here, 0.0 meters. All right, our reference point. Now, what else you need is a direction to say is the positive direction or negative direction. We have to have a direction. All right, so to the right here is going to be, and usually what you do is you draw an arrow with a little positive sign or, something like that. That's the positive direction. And that's the 0 meters. So if something moves from the origin, let's say let's just say 1 meter, right? Let's say it's moved 1 meter. Its location after it moves is positive 1.0 meters. So it's moving along a straight line. I should make that note here. This is a one-dimensional coordinate system. Okay, it's just an object moving in a straight line, one dimension, the x direction, right? Two-dimensional motion would be something moving in an arc or a circle in a plane on a flat ground, right? It's moving in the x direction and the vertical direction, y direction. This is just a one-dimension coordinate system. All right, a reference point is 0. It's moving away from the origin. It's covering a certain amount of distance each time interval. All right. Well, let's keep track of this thing's motion. Let's say each one of these drawings was made 1 second apart. So at 0 seconds, it was right here. At 1 second, it was right there. At 2 seconds, it was right here. 3 seconds, 4 seconds, and 5 seconds. So it's like I started a stopwatch when the marker started rolling from this side of the screen, right? Started a stopwatch, and then I picked out where it was every second, right? That location is called the ball's or the marker's position. 4 meters, 5 meters. I'm making up that distance scale. All right, each of these is called a position. So if I say, what was the marker's position at 3 seconds? You'd say, oh, it was at 3 meters, right? Positive 3 meters. If it moved to the left, away from that starting point, that origin, we'd say it's moving in the negative direction. All right, so the position of this marker increases with time. All right, the position increases with time. So as the time goes, the position just keeps increasing, and it keeps increasing at a constant rate here. All right, so what can I do with this? Well, one of the things we do, like, is we make a graph of the object's position, right, as a function of time. As a function of time. Position would be in meters, time would be in seconds. I'm writing out the full names here because I'm not going to introduce the variables quite yet. Position, we're going to use a specific variable for, and time, it's going to be a lowercase t. But we'll talk about that a little bit in class. So, position, okay, I can make a scale here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is the positive direction on the scale. There's positive. And time, 1, 2, 3, 4, 5 seconds. So, at 0 seconds, it was at 0 meters. At 1 second, it was at 1 meter. At 2 seconds, it was at 2 meters. At 3 seconds, it was at 3 meters. At 4 seconds, it was at 4 meters. At 5 seconds, it was at 5 meters. All right. And like we do in science classes, we put a fit line on that. Right? Mr. Roboto taught you that in earth science, how to draw fit lines. And that fit line tells us some things, right? It tells us that position increases at a steady rate as time goes on. This is what we call a position versus time graph. All right, position versus time graph. And from that graph, we can, believe it or not, we can really learn quite a bit. You know, I can read the graph and just say, okay, from 2 to 5 seconds, it went from 2 meters to, it went 3 meters forward, moved 3 meters forward. On average, I could say it went 1 meter every second. Rise over run. Slope, rise over run. That means something, right? It's a line. Y equals mx plus b. Y equals mx plus b. Y is the y variable. M is the slope of this line. X is the variable that's on the x-axis. B is the y-intercept. Those letters all mean something. Y equals mx plus b. It means something. My handwriting's getting messy. Here's my second video of the night. I'm going kind of fast. So y equals mx plus b means something. And we'll talk about that a bit more in class. What does y equal mx plus b mean? Well, we're gonna do a little lab. Y, position x is position. The position of the object equals the slope of the line. X is time, multiplied by the time, plus b, y-intercept. Y-intercept. The generic kind of definition of y-intercept is the value on the y-axis at the x-axis equal to 0. So it's the position when the time equals 0 seconds. Your position when time equals 0 seconds. That's the physics way of saying your starting point. Where was your starting point? This one started at the origin. For some reason, I had 2 markers and I let them go, and I let one start 2 meters to the right of the origin. Then that marker starting position would be positive 2 meters. So, again, position, it's always relative, right? It's always relative to that declared origin. And you pick the origin. You always pick the coordinate system in problems, right? And as you get more advanced, you'll see choosing the coordinate system becomes important. All right. I just want to give that, maybe watch that video a couple times. Really, the big takeaways are position. All right, it's location in a coordinate system. Or really it's your location in space, your physical location. Speed, really its average speed is kind of your distance traveled for a certain amount of time. All right, that's the kind of two main takeaways. All right, position is location in a coordinate system, and average speed is distance over time. And that's going to be enough to get us started for now. All right, talk to you guys later. Have a good one.